Hello YouTube time.
Hello.
What do we have on the bench today?
We have some computer developer systems.
From ENL, my favorite brand of breadboard system.
Microprocessor trainers.
Hello and welcome back. If you follow the channel, you know that I love breadboards, in particular the vintage ENL ones. I love my simple triple power supply BB4, great for prototyping analog circuits. Similarly, I adore my conveniently sized DG Designer, which I tricked out with some 7 segments LED displays for digital circuits prototyping. And my current favorite is the Monster Elite 2, complete with powerful variable supplies and a full-fledged function generator. It is currently doing telemetry demodulator duty in the Apollo Communications setup. It helps that ENL is the inventor of the modern breadboard, the familiar one with the 0.1-inch hole array, the horizontal power rails at the top and bottom, and the middle trench for the ICs. Yep, that's an ENL patented design. But in terms of sheer innovation, the MMD-1 tops them all. It does not look that impressive, nor is it well known, but in my opinion it should be. It was quite novel for a 1976 design. First born as a Dynamicro and published in Radio Electronics, it was a brainchild of John Titus, who is probably more famous for designing the Mark 8, one of the very first personal microcomputers based on Intel's previous chip, the 8008. The MMD-1 was much more compact and elegant, combining a prototyping breadboard with what was arguably the first single-board personal computer. It was powered by the new Intel 8080 processor, the same 8-bit chip that was at the heart of the much larger and much more famous Altair 8800, released just a year earlier. The Altair arguably kicked off the personal computer revolution and for sure the birth of Microsoft. But as we will see, this diminutive ENL MMD-1 with a little helper circuitry on this breadboard can do just as much as its famous Altair cousin. If you stick with us, we'll show you how we ended up running Altair Basic on it. Yeah, so those are MMD-1s, Mini Micro Designer 1, and ENL is the inventor of the breadboard. Did you know that? They invented it. It's actually, I have my Monster one that I worked on with Ken, so this is now being used for the Apollo setup. And they made an 8080 based development system. There were whole entire books written about it and tell you what the microprocessor is. This one I showed you in the bug book. At the back of the bug book there's this, and you recognize it's actually a graphic of the system. And this is not a mere coincidence. Both the book and the kit were conceived by the same people for the purpose of training engineers to the new art of microprocessors. If you flip to the back page of the bug book, you'll find a picture of John Titus, the designer of the hardware, and David Larson, his partner in crime in the writing of the bug book series. We've had the honor to get them both on Zoom, interview coming up in a follow-up episode. So if you open it up, they explain to you how to do address decoding. So they'll teach you how to do a little circuit that uses a TTL chip. So they'll take you through all the TTL chips and make some experiment with them. So you learn digital electronics. This one has even the, I think they have, look at that.
Yeah, look at that.
You have the whole TTL book.
I like the displays that you had a couple pages ahead.
Yeah. So, and they used this display because one of the failings of this, and they made it low cost, it was on the LED. So the first thing you do is add displays to it. And they recommended this HP display. And as luck would have it, one of the examples uses an HP Intelligent display, which of course I have. Guess what we're going to wire up soon. Oh, by the way, we have 2. How did I end up with 2? I bought this one. USPS lost it.
Buy 2, get 1 free?
No, USPS lost it.
Oh no.
So I bought another one, which is in way poorer state. And then this one showed up 4 months later, from Georgia, of all places.
Wow. Yeah, this one's got a little bit of dust on it.
So yeah, so I end up with 2. So yeah, so this one is in very poor shape. So you could desolder it entirely, clean it up, resolder it, which is the problem. So we'll do it like we restore an old car. We take it all apart. But this one, I think, where I'll work on my PLL for the Apollo stuff, on my other ENL setup, you might be able to get it up. It's missing a few chips.
Yeah, so the I/O decoder and the keyboard encoder, they're missing some
Right,
chips.
right. And I had them in my collection, so I found them here. Also, this, you know what PROM that is?
It's 1702.
1702. What's the 1702? It's the first PROM ever.
Yeah.
Right. So how Intel invented it, right? The first EPROM.
Yeah, a little challenging to program. You can't just plug this into a regular off-the-shelf programmer because they take extra voltages.
Yes, but basically it's the Intel, they were doing research on polysilicon gate and MOS, and they found by accident that the oxide would trap charge and that you could make a PROM out of it, and then if you shine some light on it, it will just untrap the charge, and they turned this happy accident into the erasable PROM. So each of those early PROMs, there are 256 bytes.
It's basically a text message.
So you have 2 of them, and then I think there's also 2 Intel chips that do the memory, there are SRAMs. And
yeah, there's 4 of these on here. I think they're a nibble wide though, so
I thought it was 512 PROM and 512 RAM. So that's the clock chip, that's by Intel. You know, it makes the phase of the clock.
And this is very similar to the clock chip that wound up in the IBM PC. Very much in that.
There's the Intel bus drivers.
Yep.
This is just glue logic, not very much to it. The I/O decoder is to give the address to these. It's just the absolute minimum.
And the keyboard too, which presumably has some hexadecimal and some...
No, octal.
Oh, is it octal?
It is it goes 1 to 7, then it has the H and L register for the processor, and a go and a store, a reset, and ABC that's not hexadecimal, it's unused. It's for you to use.
I was going to ask you what Hulgus Rabka meant, but it sounds like you already know.
What?
What Hulgus Rabka means. So it says right here, Hulgus Rabka.
Oh. So here is the brochure. And then they have another board that goes on top of it and adds everything that's the things missing. Memory, serial I/O for a teletype, and a modem for a tape drive. This is all you need for the doing the bug book experiments, and that's all the logic there is to it. They implement ports, I/O ports. Basically, it makes it look like an Arduino, right? You can turn LEDs on and off, as you can see. So clock chip, processor, the buffers, memory chip.
Promise to the
PROM. Oh, they didn't put the second PROM. And then you have all that comes through a bus at the right, so you can.
So that's the connector here on the side.
Expansion,
right
yeah,
there.
that's the one right there. The breadboard is directly wired to some signals. Actually, this one is missing the lower.
Yeah, there's a label that's supposed to go on the lower half.
Right. So you have 7 lower addresses and all the data bits and all the control bits, so you can wire up whatever I/O you want.
Minimum viable computer.
Right, and then you can do a few experiments with the hardware, right? Mm-hmm. So I'll let you go at it. See if you can bring it up.
I'll check the capacitors too, make sure they don't go bang.
Oh yeah, so the power supply is inside. You have to open it up.
Yeah, it's all built in.
Right.
I found the power supply.
Yeah, 3 voltages, 3 regulators, and there's one those are the 75 or whatever.
723 with an external transistor.
Yeah, so it can do the 1.5 amps. It's so power hungry. They could be either a kit or factory, and I wonder if it's this one is a factory one. The other one looks more like a kit.
This is probably assembled as a kit. You see these solder joints here have no flux, and I think this is a factory.
Yeah, the breadboard, they said breadboard's too hard, will be done at factory.
But everything else, like all these components here, you can still see flux residue on it. So my guess is that somebody soldered this.
I think you're right. Whomever did this, you did a great job.
Capacitors look okay.
Ready to try it?
Let's give it a shot.
5 volts.
Yeah, we got 5 volts. 12 volts. And minus 12 volts. They all look okay. I guess I could look at ripple voltage too, but yeah, that's fine. Yeah, ripple looks good.
Okay.
But I don't see any signs of life here. Try pushing some buttons, but I'm not really getting any response. I'm kind of expecting to see the ROM monitor turn on some LEDs, but I'm not seeing anything.
Let me bring you a scope.
Yeah, clock and reset's going to be the first thing to look at.
Okay, let me get the better scope.
Soon after.
Yeah, I was having issues with the oscillator not starting, and then I just pushed on the chip. Oh, there we go. Okay, let's try this again.
Oh, I see some lights. I see some LED. So it's the clock.
I'm not seeing a clock, but then if I push on the chip, I think the socket here is flaky. Yeah, it seems to be running now, so if I hit that, it's not resetting.
Oh, yeah, sometimes. It might be worse to take every chip out and putting it back together. Yeah,
that's a good call. This guy's got a broken leg.
This one could has lost a limb.
Yes, broke a leg. Oh, we got another one too.
Another one?
Yep, another one missing a leg. This one's pretty corroded. You wouldn't happen to have a pink eraser in there, would you?
A what?
A pink eraser?
No, but I have a white one. What about that?
Just something mildly abrasive that I can use in the legs. Actually, sandpaper would probably be better. These are very corroded legs.
You want what?
Pretty
2,000 or 1,000?
Yeah, 2,000 is probably good. That's fine. Yeah, this is great.
Okay. So how many bad chips?
We had 3 bad chips.
Okay, with just
broken leg.
Broken legs, okay.
Alright, so chips are replaced. Let's turn it on and see what happens. Nothing, but we do get the halt indicator, which we did not see before. So that's...
Ooh, that's weird. The only way to get out of halt is a reset.
And I'm hitting reset and nothing's happening. But I have a feeling that our clock issue is rearing its head again. So
yeah, no clock. Yep.
Yeah, there's no clock.
Moments later.
So next step, you work with the connector? Or?
Yeah, some of the sockets have loose pins on them. They're not really gripping the pins tightly. So I've been going through and tightening those up. And so it behaves a little bit better, but we should be seeing the number 3 here.
It's different.
Instead of the number 2.
Those early LEDs, they're so dim.
Yeah.
You have clock?
I have clock. I even have a reset signal.
Alright, you have clock. Alright, so that was just contacts in the socket.
And then we have a reset signal too, so if I push reset, you can see that. So that's good.
And then you lose it somewhere else?
But then it's going off the rails somewhere else.
More moments later.
It seems to work now.
What do you do?
I reseated these 4 memory chips, and now we can advance through the program counter, so you can see it counting up. So this is the address into memory here. This is not actually the program counter, but we can go in and enter some numbers. So we can zero this out.
Yeah. If you do
1, 1, 1, so this is all octals, so each is an octal digit.
2, 2, 2. If you do 7, 7, 7, you'll light them
7,
all
7,
up.
7, they all light up.
So this is actually not from the address port. This is the program in here.
Right, the ROM monitors.
The ROM monitor just shoving them into the output ports.
Yeah, so we're just writing to each of these ports. Yeah.
Okay, so the next assignment is to make a light chase thing. which we could figure out, but we could be even easier to copy from the book. Chasing the light. You want to have fun with that? So here is the test program that Tube Time is entering at warp speed. It has two parts, a main program to move a dot across the LEDs, and an over-engineered delay subroutine that is actually longer than the program itself. It's in raw machine code, and I'm going to explain it step by step. Welcome to your first lesson in Intel 8080 assembly programming. First, a word on the structure of the printout. The numbers are all in octal, which matches the 8080 instruction set way better than hexadecimal, and also matches both of our vintage textbooks and most Altair program listings. The left column is the memory address location, split into 2 bytes, high and low, each represented by a 3-digit octal number. The second column is the 8-bit instruction entered at that memory address, also represented in octal. Then we find the assembly mnemonic of the instruction, a human-readable version of what that instruction byte means, and then my comment. The program starts at memory address 003000. The first instruction is an 076, which is a move immediate A. This instruction will load the register A with the value found in the next byte, which is 200 in octal, which in binary is a 1 followed by 7 zeros. That's the start pattern that we will output to the middle bank of 8 LEDs. So we'll have the leftmost LED lit and the 7 others turned off. Next instruction is a call, which is a jump to a subroutine. The address of the subroutine is given by the 2 next bytes, in our case 100 and 003. The Intel 8080 being a big Indian machine, things are annoyingly backwards, so 100,003 means jump to address 003,100. Yes, I know, I don't like it either. The address points to our overcomplicated delay routine. We'll ignore it for the moment and continue the execution of our program after the subroutine returns to the next instruction. Now we get to an out 000 instruction. This is an output instruction, which is going to send the value of register A to the output address 000. There is nothing special about that address. It appears on the 16-bit address bus as a 00. But while it is on the address bus, a special signal is turned on that indicates that this is an I/O address instead of a memory address. It is up to your hardware to sense that signal, disable your RAM chips, and connect the data bus to whatever output device you wired up at output address 0. In our case, the MMD-1 has output addresses 0, 1, and 2 wired up to the LED latches. Address 0, or port 0 as one likes to call I/O addresses, is the middle bank of 8 LEDs. So whatever we had in register A, which was a 1 followed by a bunch of zeros, will be sent to the middle group of 8 LEDs, and the leftmost LED in that group should illuminate. This is Hello World for the MMD-1. The next instruction is a rotate right, which in our case will move our single 1 in the A register to the right. After which we have a jump to address 003002. That will bring us right back to our delay call, followed by our out instruction, which will now send the pattern rotated 1 step to the LEDs. That will step the illuminated LED to the right every time we go around the loop. When it reaches the right end after the 8th cycle, the rotated bit, instead of falling off, is carried over back to the left and the moving pattern repeats. Let's launch the program and see if it works at all, which would be a bit of a miracle if it did it the first time.
Load our starting address. Okay, so what I can do then is say L. So now we're at location 0, and then I should just hit G, and nothing happens.
Yeah,
oh, no,
it's working.
It works. Look at that. So the delay routine was longer than I expected.
Yeah.
It's running programs.
Yay!
And that's calling a subroutine.
Ooh.
Not bad for my first 8080 program.
Yeah, then you can just modify one bit and it will go faster, right?
Yeah. There's a word in memory we can edit.
Right.
Speed that up.
Go for it. Well, it works, but it's a bit slow. Let's take a look at our overcomplicated delay routine and see if we can fix that. The first instruction is called a stack push, used to save register values temporarily while you are in a subroutine. The return addresses of subroutines are also pushed automatically to the stack by the processor, by the way. Inside the 8080, there is a special register called a stack pointer, or SP, which in the MMD-1 gets initialized by the ROM to the top of memory on reset, pointing to 004000. Every time you use a push instruction, the stack pointer is decremented and the corresponding registers are stuffed onto the stack. The stack pointer is then adjusted automatically to point to the end of the stack. Here, the PSW saves the accumulator A, which has our LED pattern, and the flag word, which saves the processor state including carry, onto the stack. That's done so we don't overwrite A or the processor state while we do computations in our over-engineered delay routine. Next, we load value 144 into register B. Then we load 2 bytes at once into the pair of registers DE, which functions as a 16-bit word. So we end up with the 16-bit value 001046 in the DE register pair. The next instruction is a decrement of the DE register, taken as a 16-bit value. Next we copy D, the lower 8 bits of our DE word, into register A with a move AD instruction. I know, even the assembly is written reverse in the Intel 8080. And aren't you glad we saved the original value of A to the stack? Next instruction is a dirty trick to go around the problem that the 8080 does not have a native instruction to check if a 16-bit pair of registers is 0. Instead, we do a logic OR of A and E. If any bit of the DE pair isn't 0, this result won't be 0. So if we do a jump if not 0 on this result, we'll have effectively tested for DE not being 0 on all 16 bits. The jump goes to 003106, so we loop around wasting time and decrementing DE until both D and E are 0, at which point we fall through. At this point we start to decrement B. B is a simple 8-bit byte, so testing for 0 is straightforward with a jump if not 0. Which will get us back to reloading the pair DE again and waste a bunch more time until that pair gets decremented to 0 again. Eventually, B will also reach 0 and we will fall through, after having wasted a lot of time, to the pop instruction. That's the opposite of the push instruction we had, and it will restore the value of A and the flag word that we had saved on the stack, while doing the stack pointer arithmetic for us. Finally, we have the return instruction, which will automatically fetch the return address from the stack for us and go back to the calling program. So you can see that changing the delay is as simple as changing the values loaded in B, D, or E. Putting a smaller number in B at address 003102 looks like a good target to speed things up a bit.
So what I'm going to do is 003H, and then the low address is going to be our timing byte at 102, 102L.
102, 003, 102, yeah. And then you have a 441.
Yes. So let's try 024.
It's
like to store it.
Yeah.
And now let's go back to 000L, and then we'll hit G.
Ooh, it goes fast. It's like a very bad IMSI. But then this processor could run BASIC. So it's
Yes.
it's just the power of that processor compared to chips that are around here is just a big delta, right?
Mm-hmm.
And if you surround it by the right hardware, it runs the whole, HP intelligent terminal. Yes, the Intel 8080 is the chip that powers my HP 2645 terminals. Surrounded by the right amount of memory and good peripherals, it could do quite a bit. Like we're programming the 8080.
Nice.
We feel all powerful. This is the future, Mike.
The future of computing.
Yeah. Ooh.
Now we're talking.
Yeah.